Hello, everyone, and welcome to Besen's AI webinar series. My name is Jaden Kerr, a senior software engineer here at Besent, and I'll be your host for the next 6 weeks. Thanks for joining us as we explore the ever-evolving world of AI. In this series, we'll dive into what's possible today, what's coming next, and how to navigate AI responsibly. Each session, we look at real-world use cases, practical frameworks, and expert insights to help you move forward with confidence. Today's session will explore a new approach to prompt design that goes beyond traditional methods. This session explores how combining retrieval, reflection, recursion, and context engineering helps large language models generate more accurate and reliable outputs, whether it's structured data like JSON and XML, code, or natural language. Rather than focusing on what humans want to say, this technique centers on what the model needs to perform at its best. You'll see how it can be used to build self-improving systems or to fine-tune prompts for other models. Expect practical strategies, real-world examples, and a look at how this method is shaping the future of AI development. Here is this week's speaker, me, Jaden Kerr, senior software engineer, as part of Digital, and my wonderful co-host, Stoyan Shapov, solutions lead Digital, on our talk, designing smarter prompts with retrieval-augmented meta prompting. So let's get into it. Like I said, designing smarter prompts with retrieval-augmented meta prompting by myself and my co-presenter, Stoyan. Cool. So which one do you think would yield better results? A basic thrown out there prompt, or a well thought out and structured prompt which has key features such as role, a checklist, instructions, an output format, stop conditions? I think we would all agree that it would be the latter. In today's talk, we'll be going over the state of retrieval-augmented meta prompting, which is also called RAMP, 4 pillars of RAMP, a meta decision framework, challenges and solutions to RAMP, a reference architecture of how this can be used at enterprise at scale, and Q&A if we have time. Otherwise, you can ask any questions that you have in the chat, or you can email Stoyan or myself if the email's provided on the last slide. So let's look at the current prompting landscape, and let's start where most of us began. A basic prompt, which would look like summarize this article or generate a Python function to do whatever. This is zero-shot prompting, where you ask directly without examples. And if the results weren't good enough, maybe we added a few layers, a few shot example, providing a few examples to guide the model, a chain of thought hint, encourage reasoning by asking the model to think step by step, often crafted manually by engineers or business users. And we might even throw in some extra guardrails. And that's basically prompt engineering, and it works to a point. But here's the problem. The prompts are brittle. A single word change can break them and break everything. They don't scale. A good prompt in one domain will fail in another domain. It's heavily dependent on prompt whisperers to use the right phrasing tricks, and they often ignore the real question: what information and structure does this model actually need to succeed? The outputs themselves are non-deterministic, making them inconsistent and really hard to reproduce. If we want consistent, reliable systems, we need prompts that are dynamic, adaptive, and context-aware. When you start with prompting, you just give the system direct instructions. This evolved into prompt engineering, where you've got structured instructions with roles, examples, and guardrails. Then we got meta prompting. This is where you're using a large language model to generate or refine prompts which are then used as the input into another or even the same large language model. And then we've reached retrieval-augmented metaprompting. It's an adaptive system with retrieval, reflection, recursion, and context. As an analogy, if a static prompt is like giving someone a printed recipe, and a meta prompt is like training a chef who can find ingredients, taste along the way, adjust seasoning, and make sure the dish works exactly for your and your guests' palates. People are actively trying to solve all of the complicated challenges that we discussed earlier, but they're doing it in really complex ways, ways such as what you can see on the screen. For the purposes of this talk, we have simplified this into 4 core ingredients of RAMP. So what are the 4 core ingredients of retrieval-augmented metaprompting? We've got the retrieval pillar, which is pulling the right information from knowledge sources, APIs, and previous outputs. We've got reflection, asking the model to check, critique, or improve its own answers. We've got recursion, where we're feeding outputs back into the process until certain goals or constraints are met. And we've got context engineering, structuring the prompt so the model knows exactly what format, role, or constraints it must follow. Let's go through the pillars. Pillar number 1, retrieval. Instead of just having a basic prompt, the system grounds the prompt in external knowledge sources, not just for factual accuracy, but prompt construction. So fetching, some examples might be fetching a structured schema in JSON or XML before asking the model to provide an output. Or as you can see on the screen, you can provide domain-specific knowledge. The second pillar, reflection, is where the LLM checks its own work against expectation, reflects on weaknesses in an answer, diagnoses any prompt issues, and then adjusts the instructions themselves. This is often achieved using things like checklists, scorecards, validators, or even secondary prompts. An example would be, does this JSON match the schema? If not, fix it. Or, as you can see on the screen, instead of blindly accepting its first output, the model scores itself against a scorecard, which is the one you can see on the left-hand side of the screen. And each of these criterion get a score. If the model falls short, the system tells it to then adjust the instructions and try again until a satisfactory goal is met. For example, you might set it to need at least 25 out of 30 before it proceeds. So the goal isn't just generating text. It's to generate text that passes its own quality gate before it even reaches the end user. So notice how the LLM doesn't just say bad output. It actually diagnoses what fails and then rewrites its own instructions to improve. Without reflection, outputs can look correct but fail real-world needs. With reflection, the model becomes its own reviewer. Pillar number 3, recursion. The core idea here is that the LLM works in an iterative loop. It generates a draft, validates it, adjusts, regenerates the draft, validates it, adjusts, and repeats these steps until the output meets all conditions. Instead of a one-shot answer, the prompt becomes a process. Recursion isn't just rerunning the same prompt. It's about breaking a big problem into parts, iterating on each part until it's right, and then integrating everything back into the final output. That's how you get the results that are both high quality and scalable. And our final pillar, context engineering, is about programming the model with the right scaffolding before it even generates text. We don't just tell it what to write, we tell it who it is, who it's talking to, what matters most, and what format it must follow. Here we treat context as a programmable resource. We can filter, compress, and prioritize what goes into the prompt. Examples are embedding-based retrieval and role conditioning. And this is how we stop getting bland generic outputs and start getting responses that are tailored, consistent, and enterprise ready across different use cases and data formats. So here's the impact of retrieval-augmented meta-prompting. We've moved from generic messaging to targeted outputs conditioned on specific industry pain points, from feature dumps to quantified benefits with clear return on investment, from assumptions to evidence-based answers using retrieved data, from one-shot guesses to iterative refinement loops, and from ad hoc prompting to systematic engineered approaches that scale. If you like what you've heard so far and would like to give RAMP a go but don't even know where to start, we've reduced the barrier to entry to start using RAMP with these two online tools that you could use today, and the links are at the bottom of the screen. So there's the OpenAI Prompt Optimizer. This is an official OpenAI meta prompting tool. And we also have the GeneratePrompts.ai, a community-driven tool for iterative prompt generation, rapid prototyping, and testing. You would use a community tool for exploration, ideation, and team learning, but we would highly recommend you use official tools for stability and enterprise reliability. So let's go into a demo. So on the screen here, you can see I've dumped just a straight up prompt into the OpenAI Prompt Optimizer, and it is going through its own version of the 4 pillars. So you can also see there's an optional box at the bottom if you want to request any further changes or give the system any guidance. So it's optimizing the prompt, structuring the different sections, the constraints, the steps, adding reasoning for each task. And you can see here we've got our the results of RAMP, a enhanced prompt that we can use. And at each step, there are these icons where it will actually tell you how it reasoned that this step was required and why it was included. And if you're happy with it, you can proceed. And if you would like, you can request further changes to iterate on the output prompt. With that being said, I will hand over to Stoyan.
So I mentioned that by this stage, you might be itching to try. You might be itching for this webinar to be over so you can go and meta prompt your favorite LLM. And some of you may already be doing this. So here are a few more tips to get you started and make things easier for you. So the framework itself is not a silver bullet, and therefore it needs to be tailored to the situation in hand. So use our meta decision framework to decide which pillar is most appropriate and in what order it should be applied. The first question we ask ourselves is about how much do we know about the domain. If we are high on information availability, then we can go straight into context engineering. If we are low, then we might have to do some more retrieval from our sources and do some recursion to allow for some planning. At quality requirements level, we ask ourselves, how perfect does this need to be? If it's something important like a legal document, then all 4 pillars are appropriate. However, if it's a timesheet reminder email, then perhaps the standard approach of reflection and retrieval might be sufficient. If we're under time constraints, we may want to parallelize some of these processes. So running retrieval and context engineering in parallel to speed things up. But if it's an exploratory type of situation, then we can just start with recursion and see how far the rabbit hole we can go. At the complexity level, we ask ourselves, how complex is this task? If it's super complex, then yeah, by all means, 4 pillars are appropriate, and we should apply them iteratively through at different stages. If it's simple, then context engineering and reflection are usually sufficient. The beauty of this framework is that really it adapts with you, and you don't have to use a sledgehammer to crack a nut. These are some of the things to watch out for when you're using the 4 pillars. If you give the LLM too much context, then it will get confused. It's the analysis paralysis that we experience when we are presented with the same situation. So the solution to this is to make sure that the information we provided can be scored, and so that the LLM can decide which one is of higher applicability than another. And if your system allows it, you should consider pruning the context dynamically as well. Then there's recursion depth management. So without proper controls, the system might try to turn the email that we saw earlier into a PhD dissertation. And so what we need to do here is we need to tell it when to stop. We need to teach it and by defining success criteria. The reflection loops are much like a perfectionist designer who takes 3 months to achieve a single logo. So here we need to give them confidence thresholds and iteration limits, so we don't use up too much money and time. And finally, integration challenges are always a reality. We may have our pillars having to integrate with different systems to find different information, especially if we've automated them. So it's best to standardize on the interfaces here and rely on standards like the model context protocol and the agent-to-agent protocols, so that we can make sure that our agents can communicate correctly. Next slide, please. So what we've described so far are good strategies for improving your prompts. You can just use the optimizer if you wanted to, if you don't want to do these things manually and apply the 4 pillars. But what happens if you want to use your own data? How would you go about this? Or what happens if you don't trust the optimizer, that it's not going to take your prompts and use them against you in some way or sell them to someone else? So the real power comes when we put each of these pillars, turn it into an agent, and put them all together to work based on the meta decision framework that we saw earlier. So this is a conceptual reference architecture about what this might look like. So let's walk through it from left to right. On the left-hand side, we've got a client, and this client is what we would use to interface with the system. This could be something like a Slack chatbot, or it could be a developer tool like an IDE that connects to our MCP server for connecting. We obviously need some kind of identity provider to make sure that no one else can connect to our system. And then we run into the actual heart of the system, the body, that is. The runtime is where our agents run. We can turn each of the pillars into their own individual agents, which is best practice, running agents and tools together. And we'll need an orchestrator to run them in specific order, depending on what the context of the prompt that has come in. So this is where we use the meta decision framework to decide which one should run first and which one should be called second, or whether we just let them coordinate themselves. The orchestrator itself is also an MCP server. So that's the model context protocol server, which is a fancy API that AI agents and AI applications nowadays understand, so they can know what tools are being presented and how they can be called. So we've got the runtime running the agents. The agents, however, need a few more things. The first one is obviously a large language model. And in fact, we might need more than a single one. We saw earlier that with reflection, we may benefit from other models as well. So what we've seen in practice is that if you use one model to generate a prompt and another model to query it, then you get more diverse and better responses that are scoring higher on the benchmarks. So we can also tailor here. Retrieval agents may need something that's a bit cheaper, while reflection agents can use something that's got a bit more reasoning and a bit more expensive. Obviously, each agent would require a guardrail or more than one guardrail, so they can be limited as to what they are allowed to do. And then we'll need to use some kind of a short-term memory so that the agents can share the information between each other. We don't use long-term memory in this case because we don't want to remember any of this information because it may be private, but it's something that can also be applicable here if required. Now, the most important thing that makes this valuable to an organization is that you get to use your own data sources, chunk them up into a vector database so that you can create a knowledge base that can be queried by the agents, and they can find the information that is most applicable for what the agent needs. And this is why you'd want to be building these kind of things yourselves instead of relying on a third party, because they just don't know the gold that exists in your existing data stores. Then we need some kind of a observability capability so that we can keep track of how long it takes for the agents to run and whether any of them are failing. A way to deploying it will be really handy so that we can go into a production straight up instead of just being stuck in the MVP state. And finally, we need to be able to monitor the cost of the system. So cost management is something that needs to be provided as well, because those LLM calls do add up. So how do you go about building something like this? There's so many choices out there, frameworks and cloud providers. What we've got in this slide is the components that we saw in the reference architecture on the left, and the two options that we see most often being used nowadays for Amazon and for Azure. So the agent frameworks is always a very interesting one because there's so many of them out there, and so the choice of a framework may prevent you from starting the project that you may need to start. And the answer at this stage is all of them will do the job. You just have to do the heavy lifting. And this is where the exciting part is, at least for me. Microsoft provides a semantic kernel and Node2Gen, but it doesn't mean you can't use them on AWS either. Those are interchangeable. The one that most excites me lately is Strands, just because it's the latest one on the block and it has learned a lot from the previous frameworks. It's simple to get started, but also super powerful and clean, and you can extend it as well. Then all the offerings from the two providers can really be summarized into two major themes. Amazon Agent Core Runtime and Azure AI Foundry both provide all the components that we saw before. That includes memory, knowledge bases, vector databases, as well as the models that you can use. Next slide, please, Jaden. So if this is of interest, then consider engaging us for the Versent agentic experience. This is a 4-day workshop where we meet in person like the good old times, and we talk through your worst case scenarios and all the things that keep you up at night so that we can understand how we can possibly solve this through agentic and Gen AI. We can then prioritize things, we can look at how we can build it, and we even provide a prototype for you using your own data. So that's something that's in the works for us, and we'll be more than happy to talk to you about it.
Thank you, Stoyan, and thank you to our audience for joining today's session. If you're interested in the workshops, you can scan the QR code on the screen, and if you have any, or you can reach out to ai@versent.com.au. If you have any questions or follow-ups about today's topic, you can reach out to Stoyan or myself at the emails on screen, or you could even reach us on LinkedIn. So what's next in this series? We have 5 weeks to go. Next week, week 6, the 18th of September, we have our speakers, Gareth, Principal Solution Architect, and Sanya, an Associate Consultant, on their talk, Transform Your IT Operations from Reactive Support to Proactive Intelligence. In other upcoming sessions, we'll dive into topics like AI-powered customer experience, Gen AI use cases in healthcare and operations, and how to build secure, scalable AI systems. So keep an eye out on your inbox for the next invite. Thanks again for being part of the Vicent AI webinar series. We look forward to helping you unlock the potential of AI safely, ethically, and with impact. I hope you have a great day, and we will see you next time.